When a car hits a particular bump on the road, the car's shock absorber is compressed 6 inches and then released. The vibration of this brand of shock absorber follows a damped harmonic motion with a frequency of 2 cycles per second. The damping constant for the spring that makes this shock absorber is 2.3. Part A, we're asked to write the equation that describes the displacement y of the shock absorber from its position of rest as a function of time t. Assume t equals 0 is the moment the shock absorber has been fully compressed and starts to oscillate, which means at time 0 the displacement is 6, which is why the graph contains the point 0, 6. Next, because the frequency equals 2 cycles per second, the period is equal to 1/2 of a second. If we take a look at the graph over the interval from 0 to 1/2 of a second, and then break this interval into 4 equal subintervals, it does follow the pattern for the basic cosine function, even though it is damped harmonic motion. We have a point at the max, a point at the midline, a point at a min, a point at the midline, and a point at a max, which indicates we'll be using the damped harmonic motion function involving cosine, not sine, which is f of t equals a times e to the power of negative ct times cosine of omega t, where c is a damping factor, the absolute value of a equals the initial displacement, and 2 pi divided by omega equals the period, and therefore omega divided by 2 pi equals the frequency. So in our case, we know the absolute value of a is equal to 6, and because we're starting at a max, we know a equals positive 6. The damping constant equals 2.3, and therefore c equals 2.3. And now we need to find omega. Let's find omega using the frequency, given omega divided by 2 pi equals the frequency, which is given as 2 cycles per second. This indicates that omega divided by 2 pi equals 2. To solve for omega, we multiply both sides by 2 pi. Simplifying, we have omega equals 4 pi, which indicates the equation that describes the displacement y as a function of t is y, or y of t, equals a, which is 6, times e to the power of negative ct, which is e to the power of negative 2.3 t, times cosine of omega t, which is cosine of 4 pi t. And now let's look at parts B and C. Part B, how long does it take for the amplitude factor of the vibration to reach 0.7 inches? The amplitude factor is a times e to the power of negative ct. We'll first solve this algebraically and then check it graphically. To answer the question algebraically, we need to solve 6 times e to the power of negative 2.3 t equals 0.7. First, we divide both sides by 6. Simplifying, we have e to the power of negative 2.3 t equals 0.7 divided by 6. Next, we take the natural log of both sides of the equation. On the left side, we apply the power property of logs and write the left side as negative 2.3 t times natural log e. Equals natural log of the quotient of 0.7 and 6. On the left side, natural log e equals 1, leaving us with negative 2.3 t equals natural log of the quotient of 0.7 and 6. Last step, divide both sides by negative 2.3. Simplifying, we have t equals natural log of the quotient of 0.7 and 6, all divided by negative 2.3. Now we'll go to the calculator, evaluate the quotient, and also check it graphically. On the left, I've already entered the quotient, which is approximately 0.93. If we take a look at the graph, I've already graphed the damped harmonic motion function from 0 to 4 seconds, as well as y equals 6 times e to the power of negative 2.3 t, which is the red dashed curve above, and y equals negative 6 times e to the power of negative 2.3 t, which is a dashed red curve below. I'm going to go ahead and turn off the damped harmonic motion, as well as y equals negative 6 e to the power of negative 2.3 t, and I'm going to turn on y equals 0.7. Notice the point of intersection does have an x value of approximately 0.93, which means our answer is 0.93 seconds. And then for part C, if a smooth ride is defined by a displacement of less than 0.7 inches, after how many seconds from hitting this particular bump will the car ride be smooth again? We're told to solve graphically and round to 2 decimal places. We need to be careful here. When we say a displacement of less than 0.7, we really mean the absolute value of the displacement being less than 0.7. So going back to our graph, let's turn on the damped harmonic motion function. We already have y equals 0.7 graphed, but we also have to graph y equals negative 0.7. Anywhere between these two horizontal lines, we can say the absolute value of the displacement would be less than 0.7. So we're looking for the time after which the absolute value of the displacement is less than 0.7. Well, this rightmost point of intersection here is the last time where the absolute value of the displacement equals 0.7, which means any time after this, the absolute value of the displacement will be less than 0.7, and the ride will be smooth again. Rounding to 2 decimal places, we have x equals 0.81, which means after 0.81 seconds, the ride will be smooth again. I hope you found this helpful.